I guess we should start. Just a gentle reminder that we have homework 1 has been due, so the homework 2 has been released. It will due, I think 14 next Friday at the end of the day. So same as the homework 1. So if any problem, let me know or the TA know in terms of submission issue. You should ask for TA. So today we will be covering random variables. In particular, we probably able to finish half of the discrete random variables. Okay. So after the weekend, probably we should remind ourselves what have been covered so far. Okay. So what is a random variable? To recall the definition, is a function that assigns numbers to outcome. So which means that for outcome of the random experiment, you put number, right? So say the example would be you have head or tail, then you put X is head, tail, T is head, right? And head, then you could call X as random variable is number of head, then you have head is 1, then you have tail is 0. So this is what graphically represent, right? Just for each things in the sample space, and you put it in some numbers, okay? And what the number you can do is called the support, right? And if you just use a finite number of numbers, then you call it discrete random variables. If you use a continuous number, say real number, then you will become a continuous random variable, okay? So the way you use discrete or continuous depends on the context, which one's more natural, which one fits better, okay? And later you will see what do you mean by fit better. Is you want it to, the things look like what you want, okay? Some things you want to, you care about it, okay? So for example, in this case, you have HH, HT, TH, and TT, then you care about number of heads. Might be you're in a gamble that how much you win depends on number of heads. Then in that case, then finding these numbers, having a random variable number of heads will be meaningful, right? Can be say number of tails, right? That's also feasible, right? But also you can just, another case would be something like, I mean, this is not the only natural case, right? So you can think of, this is 1, okay? And all these are 0, okay? That is also a feasible one. If you think there's a gamble where only 2 heads will get you $1, otherwise you get 0, right? What might be the case is like, say, suppose a airplane, right? And only if the value of 2 engines would make the plane gone, in that case, then this would be a relevant random variable. So it really depends on actual scenario that what kind of number you want to put in, right? Because once you put a number, we want to do some calculation. So you have to make those calculations make sense. So that that's the thing we want to emphasize here. Okay, so and that's how you put numbers, right? And when you have many numbers, infinite numbers, right? Then you use continuous random variable. Okay. So the thing you often measure in money terms is basically all the continuous random variable, right? You're counting things, then it's discrete, okay? And there's often in a business application, there's either usually is a number you care about, right? So usually you would have a continuous random variable, but if you're looking at customer satisfaction and how many customers are coming, how many category of product they're selling, and these are discrete. But otherwise, most likely it's a stock market index, then there's something you see is a continuous random variable. Okay. Now, so I think I mentioned it last class, is our study of random variable divided in 2 parts. One is discrete, one is called continuous. And the reason that we are separating the two things is because the math tools require. For discrete, we can use our usual calculation method where you learn in high school, addition, subtraction. Okay, it's no problem because there's a discrete number, there's finite number of things you can add. That's not a problem. But when you have continuous random variable, we can't. So you will see the notation of summation integration, okay, the differentiation, but that would be similar to what we are doing. So everything would naturally carries to the continuous, okay? If you never learn calculus, you just need to remember almost everything from discrete, the operation can be transferred to continuous one. So shouldn't be an issue. So the first thing I would like to mention, I think we just probably stop here, is for a discrete random variable, how you would describe it, okay? The most natural one is called the probability distribution function or probability function. It's just a function that maps the number to probability, okay? Just like tell me what the number is, okay? I will tell you what the probability, okay? Give me the number, I give you the probability of the random variable equal to that number, okay? And the other one, which is not very useful in the discrete context, but will be very useful in continuous one, is what we call the cumulative probability function. It just, you give me that number, x, okay? This function will give you what is the random variable less than or equal to that number. So equal to is very important, okay? Less than or equal to that number. And in the other word, you can write in this way, right? It's just like, just from the definition, right? Just add up everything before it. So I just add this to your slide in case you have an old version that this is something I add, but it's not nothing new, but just the way you write it. Okay, just like this means that you're adding up, this is summation side, right? Adding all everything for the value of y, right? I mean, for anything that is less than x, okay? Just put there, okay? It will be very clear when you look at the graph. Is that okay? Shouldn't be a big thing, but you may ask why I want to talk about this, right? Because you would imagine that having the p would be sufficient for all the purpose. Yes, it's sufficient to all the purpose, but f will be naturally, when you talk about continuous, that we'll talk about f. So that's why we learn it just to know. Here is you can see we have a summation side here, okay? And indeed, that's what happened when you have the continuous integration. If the integrand, the integral of this guy change from summation to integral, and that is basically how things being done in continuous setting. But that's why I put the notation here, because when in continuous, that you can connect yourself to here. But at the moment, I think it's not, I mean, for discrete, it's not very important, okay? But you need to still know the definition, but it's not really a very deep thing. Is there any question? I think we just stop here. If no, then we just go to the example and see how they're being applied. Okay, so just have a very simple example. We have a toss a coin with head or tail, right? And number of head is the random variable. Okay, so it means just to remind you again, what we're doing here is this one, and we map to 1, this we map to 0, right? Or if you like, you have h and t is here, okay? And you have a 1 or 0 is here. Maybe just looking at look better. Okay. And that's how h map to 1, right? And t map to 0. Okay. So when you see 0 is means head, means tail. When we have head means when we have 1, that means head, right? So we have a fair coin. Okay, there's a fair coin. So how we can find probability function is very simple, right? Asking when this value would realize, right? The probability of being 1. That is exactly just ask the probability of being h. So that's why it's 1/2. Okay, that's how the 1/2 is coming. Is probability of x equal to 0 is exactly probability that head is equal to the sample we have had, right? So basically just like p, right, of 0, right, is exactly probability x equal to 0, right? And this is just probability we have a head, right? And in a fair, for a fair tail case, this is what we have, okay? So we have this, and also the similar way you can convince yourself this 1/2, right? Because x equal to 1. Oh, sorry, I make a mistake. It's not a head, it's tail, right? Because, sorry. Okay. And when you have x equal, maybe I just do it here to make sure that it's perfectly fine. P of 1, right? That is probability that x equal to 1. That is probability of the head, right? For a fair con, this is 1/2. Okay. So that's how you get the P there. And how you get F, right? F is rather simple. We just look at this thing, x equal to 0, and look at anything that can be less than 0, nothing, there's only 0, right? So this equal to itself, right? 1/2, right? And in this case, I use blue one, right? Remember the notation f of x, in this case f of 1, right? It's asking the probability that x less than or equal to 1, right? Then actually this is just, you can use actually just 0 and 1, right? Just probability x equal to 0 plus probability x equal to 1, right? This is just P of 0 plus P of 1, right? So it's 1/2 plus 1/2, that is 1, right? So you can take in the table manner. In table, you just go up, right? And check the table. 1/2 is there, and add anything before, right? So 1/2 plus 1/2. Is that clear how you get the big F? Of course, we will talk about the graph, then probably it will get easier. Is that clear how you get? I mean, P I think is easy, right? P you just count all the thing, right? F you just look at the table, you go up and go left, right? You go up and see what the number and add everything on the left. Is that clear? Okay. And look at the diagram and probably help you a little bit easier. I guess I don't need to explain why you have this, right? Because it's two outcomes equally likely, 1/2 each, okay? And here is how you do the F, right? So look at 0, okay? Let's go back to this is F, right? Look at the P and see what the number is. This is 1/2, okay? And you try to add up anything before it, okay? There's nothing in front of 0, so that's by itself. There's nothing new here, okay? And look at the case in this 1, right? You should put here, okay? And look at what is before, okay? There's only 1/2 here to move up. So that's how you get this the diagram, okay? Is that clear how you get it? Is that okay? I hope that is nothing DP. I think the color is very obvious what's going on. Okay, so let's a little bit challenged here. Somewhat more challenging. I think we have a sample space of head, tail, head, tail, all right? Number of head, right? So the random variable is, just to remind you what's going on here is this one. Head is 2, right? Head, tail, and tail head, they just go to 1, okay? And tail is go to 0, okay? This is what this line means, right? This line means the following, right? Head is 2, or head, tail is 1, tail is 0, okay? The question is being what is, right? The first one, right? The first one, why this is 1/4? So P of 0, right? Look at this, it's just tail. So just asking when you have tail, okay? Tail is actually, for a fair con, is 1/4. All right, so that's how you get this first entry here, okay? Look at the second entry here. Why you get 1/2, okay? Note that P equal to 1, okay? Have two meaning, right? You have to say is HT or TH, right? It's either HT or TH, okay? And do remember that TH and HT are mutually exclusive, right? They cannot happen at the same time, either one way or the other. One happened, the other can't, right? So remember when you are OR means that the union, right? Or union, if you like. And that means that this is just adding, right? That's probability of HT plus probability of TH, right? Because that is the addition rule, right? Because the interset is empty, right? TH and HT is 0, right? Just to remember why this is true is we have, let me write here, is because of probability of HT and TH is 0, right? This is coming from the addition rule, or this is basically coming from the axiom 3, right? Just they are mutually exclusive, just you can add them, right? And each is 1/4, so that's 1/2. Okay, is it clear how you get 1? Okay, then for the last one, I don't think I need to show you. You know, it must be 1/4. The two way to do it is actually refer to HH, right? So that is basically that how you get this number 1/4. But also you know that X can only be 0, 1, or 2, right? So you can use the complement rule, right, or the partition rule, or total probability rule, as you like. Three things add up must be 1, right? So you calculate the first two, the last one must be 1/4. Okay. So regardless of which way you do, you know the last outcome. Is that clear what we're doing? Okay. So lastly, why this is 1/4 here? Okay. Because you just look at this number, right, and go back, you don't have anything, so that's why it's 1/4, right? And you may ask why this is 3/4, right? Just add, go up and go back, right? So I just write for this one, right? F of 1, right? By definition, it's actually this guy, right? X less than or equal to 1, right? And you only have two outcomes, so just basically X equal to 0 plus X equal to 1, okay? And of course, you will have something like X to be little bit, I mean, tedious, but probably you don't need to say it. Not equal to 1 or not equal to 0, right? And the things that are not equal to 0, there are many things, right? There are many things there, right? So, but they are all 0, right? So that's why this one, right, is 1/4. This one is 1/2, and that's why you get it, right? So this is 0 because X equals, say, 1.5 is nothing, right? It's the probability is 0, right? X equal to 1 point something is nothing. So that's why X less than 1 you can ignore, right? Not 1.5. Say X equal to 0.7, right? There's no such probability. This is equal. This probability of this is 0, right? Probability that X equal to 0.5 is also equal to 0, right? So only less than or equal to 1 only have two things that is meaningful, is 0 and 1, right? So that's why you can simplify from less than 1 to 0 or 1, right? And 0 or 1 basically just addition rule, right? So that is the reason why you have 3/4. And the last one would be trivial, right? Because everything must be less than or equal to 2, so it must be 1. Okay. So I hope that is clear. Is that okay? I mean, there's nothing deep here, nothing new here, but rather you just need to know definition, and that's it. Okay. And this is the basic thing you have to describe your random variable. And as you can see from this table, either you're given P or F with the same thing. Okay. The reason why we do this exercise is to showing you that usually we do P for discrete, right? We do F for continuous. Okay. But this example just shows you can change from one way to the other, right? You can move around. So if I give you the second line, so I give you the third line, F, you can always go back to, you can calculate the F, calculate P, right? I give the F, you can calculate P, right? Now here I just give you P, you go to F, right? But you can easily see that I can come from I give you the F, you can go back to P. Right? Do subtraction, right? If you subtract 1 and 2, you get 2, right? You subtract 1 from 0, then you will get the 1 entry, right? So that is how you can change from each one to the other. Okay, I mean the easiest thing to see how they change is look at this diagram. See for yourself how they change from each other, right? Say, first I tell you how you from P to F, then you can see how you F from P, right? So if you stack the first one to the second one, give you this one, right? Right, and of course, if this is itself, so just put it here, right? And if you stack the three thing here, you get the last one, right? That's how you go from the left to the right. Is that clear? I think the color is very clear. Just successively stacking. Is that okay? Okay. So let's go to the other way around. Okay. You go in this direction. Okay. From F to P. Okay. You will see if you subtract 1 and 2. Okay. Subtract, you get the 2, right? And if you subtract, you see it's blue, okay? You subtract the second column to the first column of the F, you get the second column of the P, right? And lastly, if you try to subtract the yellow again, the first to nothing before, but it's basically itself, you just go to the P, okay? So I hope it's rather clear how P and F, you can just know how to swap around, okay? Because it's hard to think in continuous random variable, but if you have a intuition how it works for discrete, the same thing happen for continuous, okay? Because I will skip the interpretation of continuous. I mean, I just talk about some integration or differential idea, but everything is just goes on. If you can imagine, you have many columns, right? Then become continuous. So everything will hold, okay? But you would have to imagine that the why it works, you have to go to the calculus, which we don't cover in this class. But okay. Is there any question before I proceed? Okay, I hope it's very clear how you can describe your random variable. Okay, and we will be using P from now on, at least for the discrete random variable. F, we will just keep in the background in your mind. We will use it again when we talk about continuous random variable. So for the moment, we just look at the P. Okay, we will use the P and how the P can be useful for our context. Is that clear? Okay, so now we are going to look at how P is useful in terms of doing calculation. But before we go, we just one technical note here is, okay, so let's see this example quickly. I do a fair die. You have sample space is 1 up to 6. And obviously, a most sensible thing is to consider a random variable is took the face value as given, right? So basically, the random variable, the sample space is already 1, 2, 3, 4, 5, 6, right? But you're just mapping this to 6, mapping this to 1, just map whatever number to there, okay? And of course, this is not the only choice you can make, right? You can make, say, 1, 2, 3, you just face 1, 2, 3. You can always map to 0, and 4, 5, 6, you map to 1. When you want to do that, maybe you're betting on big number or small number. If you bet 1, 2, 3, you get no money. You are betting on large number, you get $1. In that case, this would make sense, okay? How you assign the number is up to you. Doesn't really matter, but it has to be meaningful. Otherwise, why you put number there, right? So in that case, I mean, focus on the most natural one, the face value. Then you have each one comes out equally, so it's 1/6 for each one, right? And in that case, the F is just adding up, right? So I hope this is very clear how you get the F. I mean, is that okay? I'm not going to explain this one, okay? What I want to focus your attention on is we have been drawing things like this, right? Like the bar chart, okay? Indeed, when you look at advanced mathematical, a statistical textbook, they will not draw like this, okay? You will see they will draw in this way, okay? This is the thing you will see in the book. The reason is being that when you actually draw this function, okay, only the exact value of 1 would get the value of 1/6, right? And any other number there will be just 0. Okay, so that's why when you try to read the textbook of intermediate statistics, you will see this kind of graph, right? Because all other cases are all 0. Okay, I just put it here because when you read further, the graph you see, they don't do the bar graph. This is the way they draw. Okay, but that being said, we are in business school, right? You are doing it for the business presentation. I don't think the boss will be happy you see this graph. Okay, your client will not be very happy to see this one, right? Although this is the correct one, you would still present this to them. Okay, so that's why in the slides or the textbook or other textbook you're having, or my textbook, you will see we're not doing this one, right? We are not doing the technical one. We're doing the next technical one. Okay, but keep in mind, for function itself, it should look like this, right? This is what actually you see in your high school math class, right? But this is sufficient for purpose, okay? And you do application, this is something to draw, right? Unless you want to convince your boss is an engineer, okay? You become a data scientist, that might be the thing you should draw, okay? Because you would be doing a lot of advanced math technique that, okay, you should be more careful, okay? And similarly, when we write f, is something we draw in this way, right? From 1/6 up to 1, okay? This again, the way you can present to your client, the business setting, to your boss, that's no problem, okay? But you do note that there's a lot of thing missing from this diagram here. Is what are the value of this value here, right? In the probability function, they are all 0, right? But you know that they should look like this. Why? Because the f of, say, 1.5 is same as f of 1. Why? Because this is what? Probability that x less than or equal to 1.5, right? And this is probability that x less than or equal to 1, okay? And there's nothing between 1 to 1.5, so they're the same. Okay, so that's why you should look like the step function in the math you call, okay? But as I said, this is very technical, okay? So that's why when you look at the textbook, okay, this is what you will see, right? This is actually what you look at textbook, they actually draw in this way. If you look at more mathematical textbook, okay? I'm not saying that you should draw in this way. I mean, you can draw in this way. That's definitely fine. I mean, everyone who knows statistics will be clear they're the same, okay? But especially for those who are doing the quantitative finance, and then you should know this is the wing you should draw. But if you are doing just so in the business world, that's fine. That is definitely a good one. Any question? This technical point I want to mention, okay? Although we do a lot of things in a more informal way, but you should know the formal way. I mean, you don't have to do it the formal way in our class, but you have to know there exists a formal way to do it. Okay, just like why we learn probability, we learn axioms, how we define, but probably you would forget, but you need to know there's a formal way to do things. Okay, it's not useful for any business world, but you should know how the background behind. Okay. Now, if there's no question, then I would want to direct attention to the two things before break we will call expectation and variance. Okay, and you may ask, okay, what are we doing here? Okay, what are we doing here is basically borrow our knowledge from topic 1, okay, which is called summary statistics, right? We learn mean and variance. Okay, actually we learn more. We learn kurtosis and skewness as well, right? The shape, the interquartile range, those kind of things. Actually, you just finish a homework one, then you should remember what we are doing. Okay, if you submit your homework, right? And the question is being, what were we doing here? Okay, why we want to connect the things here? Okay, with a random variable. Okay, a random variable, say random variable x, right, is what it is doing. Right? Remember, x can have some value, maybe 1, 2, 3, or some value, right? And this some value comes from what? This some value comes from a sample space, maybe head or tail or some other outcome, right? So the thing is, okay, if I assign number to this outcome, okay, and the question is, okay, can we do something about the numbers? Okay, in particular, is the mean, okay, or variance of this random variable would have meaning. Okay, so the idea is the following. Okay, remember the idea of probability. Probability is you have the classical definition is you repeat many experiments, right? Look at the relative frequency, right? How many outcomes that are favorable to the outcome over how many experiments you have done, right? We can ask the same question hypothetically in our mind. Okay, so just remember just look at the example. We have the following, right? Total contour times, so head, tail, tail, head, tail, head, and tail, tail, right? The random variable we're going to do is this map to 2, this 2 will map to 1, and this is mapped to 0, right? That's how this example we have, okay? So imagine that you would do this experiment in your mind, okay? So so you just repeat this ton toasting, right? There will be, we say, suppose you do 4 million times, right? You should expect 1 million will be head, right? 1 million will be head, tail, 1 million will be tail, head, and 1 million will be tail, tail, right? So that why it is the case? Because if we assume, right, that the fair con, this will be each outcome equal likely, right? And we have been saying this probability, right, of this, right, x equal to 2, right, is 1/4, right, or p equal to 2, right? P2 is 1/4, right? And P1 is 1/2, right? P0 is 1/4, right? So this is what we have. And then if you try to look at the experiment again, right, you will have, if you record the experiment outcome of 4 million, this experiment, right, you have 1 million of 2, right? Because every outcome you have is XX, XT, TX, and TT. You are not recording the exact outcome, but you are recording according to random variable, right? So you have 1 million of 2, 2 million of 1, and 1 million of 0. Suppose you have 4 million of this experiment. Is that clear? Let me repeat the statement. Suppose you have 4 million of this exercise, random variable, random experiment, right? You have 1 million of 2, okay? 2 million of 1, and 1 million of 0, right? And given this data, this is data, right? Just numbers, right? You can calculate mean, calculate variance, and so on and so forth, right? Then what's the mean? Mean is exactly this number. Why is the case? Just look at this question. You have 2 millions of 1, right? So you have 1 million of 2, so times 1 million, right? And you have 2 million of 1, right? So it's 1 times 2 million, okay? And you have 0 times 1 million, right? And you calculate mean, you have to divide how many total number of experiments you get if you divide by 4 million, right? Then you look at this, 1 million over 4 million is what? It's exactly P of 2, right? So that's how you will get the expression. You multiply the value of random variable by its probability function. That's P of X. Okay. P of X is relative frequency, right? Because probability can be considered as relative frequency, right? And that is how the mean, what the mean mean, right? Right? It's a weighted mean, right? But weighted mean is weighting by relative frequency, right? Just exactly the meaning of mean. Is that clear? So if you so you will see that expectation is exactly a mean if you repeat this random experiment many times, okay? And that's how we use this, right? Because P of X, right, is exactly, you look at the ratio, right? Is that clear what we are doing? Okay, it's exactly the mean, okay? So the expectation is exactly the mean if you repeat this experiment many times, okay? So let's see, I see not everyone is convinced by this, so let's see this one example, okay? This black one. So you toss a coin once, okay? Let's make a simple one. So X is a random variable that represents the number of heads. So it's either 0 or 1, right? And this is fair. So that's why it's either 0 or 1, right? It's 1/2, right? So that's the case, okay? And the case you have toss a coin 1 million times, right? That means that you expect 500,000 head, 500,000 tail, right? I don't think that should be an issue. So it's a fair coin. So if you actually record data, right, head is 1 and tail is 0, then you have a 500,000 0, 500,000 1, right? Because head is 1, right? Tail is 0, right? So in that case, what is the mean of this observation? This is data. Data is 0 or 1, right? Then the mean is you add up 500,000 0 and 500,000 1 over 1 million, because that is divided by n, right? How many observation of them, right? And you can do the 0 times a million, right? Because 0 times 500,000, right? And this is 1 times 500,000, right? And 500,000 over 1 million. How it come from this? This is just probability, right? You define probability as the relative frequency, right? It's 1/2 times 1/2, so that's the mean is 1/2, right? So the expectation of this random variable is just 1/2, okay? So you can see the expectation means is if you just repeat this random experiment, you get all the X, right? You have a very long run, you get the average, should be same as this guy, okay? And we would denote this is called mu X, or simply mu, because if you X is very clear, sometimes simply just mu, okay? This is called expectation, okay? If you learn, this is something you might have learned it when you're high school, you do M1 math, if you have learned it before, but that is exactly what you learned in the high school. There's nothing new if you have learned it. If not, then it should not be deep, just the random variable, you just keep doing the experiment. This is, you record the number, calculate the mean, that's what it is, okay? And this is here is a weighted mean, is weighted by the P, okay? Probably you ask why I don't, if there's a weighted mean, why don't I should have this, right, as a denominator? The reason is that this is 1, right? All the probability add up to 1. So that's why we just do that, okay? Now give you some other example. What's number of head, okay? Here just very simply just 1/2, 1/2, right? Because the others like this, you just have to do this. X is 0 and 1, and P of X is 1/2, and that's 1/2, right? So basically just 0 times 1/2 plus 1 times 1/2. Okay, that's how you get this, right? When a fair die is something very similar, X is equal to 1, 2, 3, 4, 5, 6, and P of X, right, is just 1/6. 16, 16, 16, 16, 16, right? So what you do is just this multiplied by this, right? Plus, okay, plus this multiplied by this, right? Plus this multiplied by this, and so on and so forth, right? I'm not going to do it for each one, but you know how, that's how you get the expression there, okay? So you roll a die, right? Actually it's 3.5, right? Expect to be, right? So if you're trying to guess what is the F, if you roll a die many times, the average of those number is 3.5. Okay? Is that clear what we're doing? Okay, just same as the mean thing, but just you reverse the ideal probability. Okay? The probability just like you from experiment, okay? You get probability, right? Now just reverse the process in your mind. If I know the probability, right? Can I get back the data and calculate the mean? So that is it. Okay? Is there any question? Okay? Little bit uneasy actually when I first learned it. I find it very not that easy, but it looks like everyone seems to be very happy, so that's fine. Seems to be okay without any issue, because when I learn it, I just feel, what's that? I mean, what's expectation? Why don't we call it mean? But yeah, that is not mean, but the way they mean, so that's why we don't call it mean. But sometimes we are too lazy, we just call it mean. But I don't want to define. But sometimes people who are mean of X is actually expectation. But anyway. So before we break, I think we can do the variance of the break. But I want to finish this linear property of expectation. Okay. So one of the convenient thing of expectation is let's say what we call linear property. Okay. Linear property means that there's a several things you can see here is if you multiply, say, the expectation of a constant A times X, you can have take A out, okay, and times this, okay? And probably you would ask what I'm doing here, okay? So this is a very convenient thing, is simplify your calculation. Why? Because suppose X is a return of say, a particular stock, okay, for one share, okay? Do we need have the random variable for every number of shares? Do we need a random variable for 2 shares, 3 shares, 4 shares, 5 shares? Okay, no, we don't. It means that this is proportion expectation. Okay, that means proportion. So if you have a big portfolio, say 10,000 stock, don't worry. You just look at one single shares. Okay, the mean return for this portfolio with 1,000 shares would be thousands, okay, of the expectation for 1 shares. Okay, so that means that you don't need to track. You can normalize things. You can only check only single share, how the price movement of single share, then that's done. Okay, and you will know later this is not true for variance. Okay, this is only true for the expectation. For variance, a little bit different. Okay, so that's why this is an important result. Although you don't see important, you see very natural, right? You invest more, the mean just multiply. Okay, so you don't have to worry about random variable for 1 stock, 2 stock, 10 stock. There's no need to worry about it. Okay, that makes things easier when investment, right? The next one will be, this is also very important, right? Suppose X is the value of your portfolio on stock. Okay, B is the how much cash you have, right? So the investment portfolio depend on the stock or cash, right? Sum of them together, right? And this tells you that you don't need to worry about how you mix your cash or stock. You can separate calculation, okay? Because the cash is not going to change anyway, so you can just focus on the stock, okay? That makes calculation easier, right? You don't need to think about things is not moving, right? And if you combine the first and second, you get the third one, right? You multiply it times it, right? It's just before you have this guy A here, but you can take out from the first one, right? So that's how you derive it. Okay, not going to go to math, but this is very natural, right? Just like you can separate your completed stock holding and cash. Okay, the last one is actually you don't need to worry even you have two different stocks. Okay, I have stock X and stock Y, right? Actually, I can separate them into two. Okay, or a bond or stock, right? When calculate expectation, I can do it separately. Okay, I can focus on a single stock of X and single stock of Y. I just need to multiply how many X I'm doing, how many Y I'm doing. Okay, so this is very convenient. Okay, note that this is only true for expectation. For variance, different. Okay, so this is very convenient on expectation. When I talk about the mean return or expected return of a portfolio, you don't need to worry about how they're related. You can do it separately. Okay, that is convenient thing. But when you go to variance, kurtosis, skewness, then things will be very different. Okay, and for our class, we only focus on mean, expectation, and variance. Okay, and that's it. We don't talk about kurtosis, skewness. This is beyond the scope of our introductory class. That doesn't mean they're not important, but just we don't have time, and they require a lot of math to handle those. But so there's no question. Then let's a break of 15 minutes, and then we'll resume. In the meantime, I'll go around to see if any question. Hi. During the break, some of you asked me what's the use of expectation, okay? And later you will see why we care about expectation. It's because expectation is indeed our best guess. If you try to guess what it is, okay? So we will do it is I think topic 5, okay? So suppose you collect the data, okay? Okay, we want to study certain thing, and then we want to get the mean, right? Or I want to know, say, what's the average income of, say, Hong Kong, okay? Then maybe you just try to get 1,000 people, okay? And try to calculate the mean. And this mean will be the best guess for the mean of population, okay? Expectation. And another example you can imagine why you care about mean is like, suppose you are a hotel manager, you buffet in your hotel dinner, right? And every day you would have to guess how many people coming, right? You would expect how many people coming, and then you have to ask how many chef, how many servants have to be there, how many food have to order, right? So expectation will be the way you measure, right? So this is how you do investment, right? Someone come to you, say, do you want to invest in this project? Okay. The first question in your mind is, what is the expected return, right? What is the return of this, right? That is the expectation. Of course, the next question would be, you just give me this project, if you say 50% of the return, right? Or 100% return, right? The next thing is, say, how risky is the return, right? How risky is the return is the variance, right? If I tell you, for sure, I give you 100% return, there's no risk, right? Variance is 0, right? There's no uncertainty there, right? If there's still a lot of uncertainty, can fluctuate a lot, then it's a bad thing, right? So that's why we learn the idea of variance, okay? We need to learn the idea of variance. Okay, variance as same as what we learned in the first topic is look at each observation minus the mean and take the square, right? And here we have to multiply probability, right? The reason is also again the weighted mean, right? And this expression, if you look carefully, has no different from the fact that if you repeat this experiment many times, calculate the mean, calculate the variance, this is what you get. Okay, let me repeat what is it doing. This variance is asking if you have this thing in your mind, run the experiment many times, you can have the mean, right? Which is expectation we get, okay? And the second step is, for each observation, you subtract the mean and take square, add them up, right? The total number of them, that's called the variance. Is that clear? And you may ask why we care about that. Variance is a important measure, right? We look about investment. Variance is the risk, right? Expectation is the mean return, right? Or expected return, right? When we learn, I think the first class, right? We want a high mean and low variance, okay? And why do we say that? Why this is a good one? Because we use the historical data to think that historical data can help us to predict the future, right? Because when you invest, you are not looking at the history, right? You're looking at what history the return is, right? You're looking at random variable when you do an investment. Looking at future return, okay? But the future return, how do we make a decision? Is think about probability, right? Think about expectation and variance. And how do we make a guess of the future thing? Look at history. The history said the mean return is this, that is give you the mean. The history variance is that is give me the variance for the random variable. That's how we do it, okay? So that is trying to tell you how we can justify our decision making based on the topic 1, right? The mean and variance and those of things. Why it works? Because historical data give us a way or clue to guess what's going on, right? If you believe history repeat itself, right? That means that the history we observe is actually the outcome from some random experiment. right? And we try to guess the probability from the data, okay? And the probability of the data can help us to guess what the expectation and variance. Is that clear what we are doing? Okay, it's looking at the future, right? How we're going to do investment. It's looking at the random variable, right? We don't know the future, right? We have to make judgment whether it's worth to do it. Look at the mean and variance of that, right? That's how we do the topic one. If you don't remember, I think it's good to get back to this one because I think it's good to know why we are doing. So if you look at, remember the very last slide, okay? Oh, sorry. We talk about okay. Remember this one? I talk about mean and standard deviation, right? And this is the historical return and the standard deviation or the variance, right? And why the historical thing can help us to make decision, right? Because you believe that the future will look as if the history, right? So you would think the future mean is same as the past mean, which is expectation. The future variance is same as the past variance, okay? So here, how we do that, because we think the past is just a realization of some random experiment, okay? And from that, we can guess what are they. And so that's why the variance is the same idea in the topic one, okay? But we need the idea of random experiment or random variable to make this decision connect it to each other, right? Otherwise, how can the past can be used for future, right? Because past have been past, right? If you think the past is different from now, then the past doesn't apply, right? But if you think there's no difference between past and now, then this can be useful judgment, okay? So that's the answer some of you may ask, how long the history to look at, right? Because say this example I have here is like mean is 6, 5. How when we get this data historical? How far back from the history look at, right? If you think the history is still relevant, you can go back as far as it's still relevant, right? If you think 5 years is still relevant, you look at 5 years from now. If you think, no, the last 5 years, some policy changes, some macro variable changes, okay? And say the company have done M&A or company change the CEO or many things, then you can just go back as little as you wish. Okay, is it clear why we are doing mean and variance? Okay, this is if you do investment, this is the thing you would want to care, right? Because this is how the data from the history connect to the now. But of course, it will be more clear when we continue our journey in random variable. But I hope this is clear what the variance means. Okay, and that's how you calculate the variance of wrong die. Just quickly a gentle reminder what we're doing here, right? Just x can be any value from 1 to 6. Okay, and some of you actually ask me why 1 to 6, because wrong die, the easiest way is 1 to 6. You can put a number there, right? You put a number, then you can calculate the mean also. But is it meaningful? I don't know, right? But this one, it do have meaning, right? It's just like if you actually got the data, you just calculate the mean. This is what you get. Okay, P of x is 1/6 for each one, and you actually can calculate expected x is 3.5, right? Or sometimes we call mu of x, right? So that's why we get 1, right? Subtract from the mean 3.5, okay? Square times 1/6, okay? So basically each value 2 here, right? Is 2 here, right? You subtract 3.5 and you times 1/6. Okay, that's how each number is being calculated. For each number, you minus the mean, okay, and take square and times 1/6. Again, this calculation is just if you have rolled the die 6 million times, 1 million be 1 million 2, 1 million 6, and you calculate the variance, same calculation. Okay, that's no different from actually you do the experiment, calculate the variance. But this one is a little bit better shortcut, if you say, okay. Is that clear what we're doing here? A question? Of course, You can ask me anytime if you are confused, but we'll be doing mean and variance basically the whole course. So I'm sure you know it. There's no doubt you know this, what's going on here. But okay. Any question? And one of the reasons why we don't talk about kurtosis and skewness is because we focus on what we call the bell curve. And for bell curve, it's always skewness is 0, kurtosis is always 3, or excess kurtosis is always 0. So that's why when we focus on the bell thing, then don't need to talk about those. Another thing you talk about the discrete case, then easy to calculate for those. So that's why we just focus on mean and variance for our basic application. Okay, it's not because they're not important. They're very important when it's not bell shape. But in our introductory class, we focus on bell curve. So that's why it's not very important to talk about those right now. But they are very important. Okay. Is there any question? If no, then I'll give you some formula for the variance. Okay. So the important formula are the second and the third one. Okay. And the first one, okay, is important for those who are in quantitative finance or who want to study further, because this is what we call a shortcut formula. Okay. Here is, instead of calculating a complicated expression, you can calculate this guy. Okay. X squared capital expectation. Okay. What does that mean? Let me illustrate here. Okay. So in the case you have 0 and 1, and say P of X is 1/2, 1/2. Okay. What's X squared? X squared, 0x squared is 1, right? 1/2 is also 1 is squared is also 1, right? So 0 is 0, right? And 1 squared is also 1, right? So the probability, right, of X squared, right, is also 1/2 and 1/2, right? So expected X squared is just 0 times 1/2 plus 1 times 1/2 is still 1/2. Okay, so that's how you calculate this guy. Okay, so basically just square everything, you calculate the expectation again. Okay, I mean, that is useful when you do actual calculation using computer, or when you are working on a proof, that will be important. So you can see a lot of proof in this chapter slides actually rely on this one. Okay, and of course I'll give you another example to show this is correct. Okay, there's an example later, a more complicated example to show this is correct. Okay, and this is a useful formula. Okay, need not remember, but you see, you don't feel uncomfortable. Okay, to be honest, when I first learned this, I feel rather uncomfortable seeing this one. I mean, I always want to prove this guy, but it's easy to prove, but we're not going to do it in our class. But that is the shortcut. Okay, and this is computational convenient. Okay, they're the same thing. Okay, we will see another example for this one. Okay, but I want to draw your attention to the second and the third line. Okay, the second line said the following. Okay, is if your portfolio, say you have stock and cash, okay, and the cash have no effect on the variance. Okay, you have more cash or less cash, have no, because the cash is not changing. Okay, if you have more cash, you just basically move the data point to backward and forward, or the point move upward, right? So that's why you don't have B here. B has nothing there. But do note the most key thing here is this: A become A squared. Okay, that is the key thing here. Is if you multiply okay by A, then you A squared. Okay, that means that if you invest 10 stock, okay, So how the risk compare to one stock? You will be hundreds times more risky than one stock if you calculate variance. Okay, and that all usually make your mind explode. Why you take square? So that's why there's one thing we care about: standard deviation, right? Because standard deviation do not have this property. If you talk about standard deviation, right, SD of AX plus B is just A times SD of X, right? So standard deviation do not explode because take a square root, right? Take a square root on both sides is just there. Okay. So if you calculate risk by standard deviation, okay, A times of X is just A times of SD. Okay. So that's the thing. The next thing I want to say here is one very important formula is if X and Y independent, okay, this is very important. Okay, we will tell you soon when this doesn't hold. We will have the variance of the two things. It's just sum of their variance. Variance of sum is sum of the variance. Okay, the left hand side is variance of the sum. This is sum of the two variances. Okay, and you will see this is in the when this whole only if they're independent. Okay, and you ask what happened if it's not independent, right? So this is just saying the variance of stock in say Hong Kong to stock in say South Africa. I think they're independent enough, so that should be fine. Or the stock market and the cryptocurrency may be just independent, so you can just add up, right? But we do know that in the world that most of the things are not independent, right? So before I just tell this slide, just is we call covariance. We don't talk about this, but we will learn this if you learn investment. Okay, if they're not independent, there'll be extra term here. Okay, that would mean that if X and Y are positively related, okay, then the variance is higher. Okay, if X move up and Y move up, right, they have higher risk. If they reverse direction, then the risk is lower. Okay, that's actually the same thing we learned in the topic 1. There's nothing new here. Okay, but just basically change everything to random variable. Okay, because that case in the old case is just basically data, right? Not talking about future, but all the formula actually hold when you talk about future. When we talk about future, we cannot talk about data, right? It's based on random variable, based on random experiment, based on expectation. Okay, although they call the same name variance, right? But now it's a variance of random variable, right? It's not variance of data. Okay, so that's why a little bit different here. Okay, you have to know this distinction. Now I want to get back to the example we have. Okay, so I'm just trying to show you this formula, why it works as intended. Okay, you can see there are two ways to calculate. This one is the classical one. Okay, this is the one that you will use based on the formula you have. And the second one, as you see, the same answer will be based on the shortcut formula. And after I go through it, you agree that the second formula would work faster, especially when data set is very large. Okay, and even you do Excel, of course, your Excel you don't have problem for this, right? But it's good to see when you do it by hand, that will be much easier. Okay. So here I have total con twice, right? I have head, tail, tail. I can number of head, right? So that means that HH is 2, HT and TH is 1, and TT is 0. I hope that now it should not be difficult for you to see this. And use a fair con. So 0 have only one outcome, so 1/4. H1 we refer to 2 outcomes, so 1/2. 2 refer to this guy, yes, 1/4. I hope at this point you don't have any issue, right? So let's calculate the mean, right? Mean will be just 0 times 1/4, 1 times 1/2, 2 times 1/4, right? That's 1. That is very natural, right? Just like total and coin twice, right? you should expect it's equal likely. You should expect one coin, one head, right? I think that should fit your intuition, right? Those are two coins, and it is fair, right? It should at least one coin is something you expect to be, right? And the variance will be just for each outcome 0, right? Look at here, 0 here, 0 here, right? You minus the mean, which is 1, take a square times probability, okay? And the second one is 1 from here and 1 from here, and take the difference and square times probability 1/2. Lastly, we have 2, which is come from here, minus the mean coming from 1 from here, okay? And square times 1/4 give you 1/2, okay? And here we can use an alternative way to do it, okay? You can calculate in the blue way, or you can do it in the orange way, okay? You have 0, 1, and 2. If you take square, it's either 0, 1, or 4, okay? How you get 0 must be 0 times itself is 0, so 1/4 is here, right? And how you get 1 square is 1, so that's why this is how you map to here, okay? And the last one 1/4, right? 2 become 4, so it's this number. You calculate probability of x squared, okay? So it's 0 times 1/4, right? 0 times 1/4 plus 1 times 1/2 plus 4 times 1/4, you get 3/2, okay? So the formula set is 3/2, okay? Minus the mean square, okay? Expected x squared, 1 square is 1/4, okay? So you can see that I don't need to subtract and square every time, I just square and just, I do expectation 2 times, right? That makes the calculation easier, okay? I don't know whether you agree or not, but this is the easier to calculate. You may disagree, doesn't really matter, because when you look at the random variable, this, when you do the proof, this is easy, okay? If you try to look at the proof, but of course, I do it because it's just useful for the proof, but I will not use this formula anymore from this class, okay? This is just showing you that this formula works. Because you may try to read the proof, I need to let you know why this is correct, okay? And we are not using this formula for this class. I mean, this particular x squared, this formula is not necessary, okay, for our purpose. But if you want to read the proof, this is needed, okay? For calculation wise, it's not very important because they are not very useful right now because you're a computer these days. So it's only useful for the proofs, but if you don't read the proof, it doesn't really matter, okay? Now go into proof, okay? So I want to finally convince you what we are doing would be useful, okay? Although everything I talk about is discrete, okay? All this formula actually work for continuous, okay? So that's why it's okay to put this as a talk about stock market, okay? Or even discrete, you can have a many outcome. So I think it's fine to talk about stock market application, okay? So we have a stock X, mean is 1%, return and SD is like 5%. Stock of Y have mean return of 5% and variance of 1, right? So stock 1 has higher return, but also more risky, right? Because SD is high, variance is higher, okay? So the question is, okay, now we assume the independent, of course, when you go to investment class, then they are not the case, right? Independent is only relevant when we calculate variance, okay? But just make it easier, okay? And this is the first assumption, make independent. And the second assumption we are making is just you equally divide between these two portfolios, okay? And why you have to work half-half, okay? How you are going to put your money, how much is going to put X, how much is going to Y, is the whole cost of investment, okay? The whole cost of investment is telling you how to mix it, okay? So that's not our goal. We just, for simplicity, to make it half and half, okay? And the question now I'm going to show you is trying to show you what's expectation and what the variance. Why we care about this is how you make the decision, right? That's how you decide is this portfolio worth going? Okay. So remember, this calculation expectation actually doesn't rely on this independence. Whether the independent or not doesn't really matter. Look at the variance, look at the expectation, right? Half of them is X, half of was Y. So you just look at the average of the return, 7 from 5%. That's it. Okay. And look at the variance, the risk measure, because the independent, half of X and half of Y. Okay, the key thing here is not just half, it's 0.5 squared. So that is very important. If you miss it, then you miss it. Okay, you make a mistake. Half of the 0.5, half of 0.1, that gives you 0.015. Okay, so look at this carefully. You will see the mean expectation, the mean returns are half of them, but the variance, okay, the variance is not in the midway, right? It's like much smaller, all right? So that's why it's sometimes it's good to mix, okay? Because why the mix is good? Because they're independent, okay? Independent, you want to mix things, right? Mixing things is good, okay? If they're perfectly correlated, then you don't want to. Mixing have no meaning, right? So independence, right? You learn that the independent, you want to mix things, right? Even though you substantially reduce the risk, right? Right? Just to repeat what I'm saying, look at the return, right? It's just halfway of these two numbers, right? But the variance is not halfway of these two numbers, right? It's way closer to the lower one, right? It's very close to 1%, right? Because X is like 5%. When you're mixing, then it's much lower, way much lower, right? It's like a slightly increase in the risk, right? From 1% to 1.5%, okay? But the expectation goes up a lot, right? So that's why you want to mix. Of course, in the investment class, you will learn what happens if they're not independent, okay? There's some covariance there, then how you mix them, how you find the optimal portfolio, okay? But that will be not our class covering. So I hope I convinced you why mean and variance are useful. That is how, when you try to invest, that's how you try to mix, right? I mean, in reality, you don't sometimes, as a normal investor, you don't actually do this calculation, right, at the back of envelope, but you do have an idea that, okay, how you can calculate the risk, right? It's just like how you mix things up, right? Is that okay? Any question? There's an example to show you. Okay. If no, then probably we will cover this common discrete distribution. Okay. So I'm not sure how much I can cover, but we will cover at least the first two for today. We have 15 minutes left. We'll cover first two. Okay. Uniform and Bernoulli. And from Bernoulli, you will basically these three actually follow almost follow from the Bernoulli. Okay, almost very similar. Okay, I mean, to be exact, I would say binomial coming from Bernoulli. Okay, Bernoulli go to Poisson. Okay, and later you will see the binomial and hypergeometric are closely related. Okay, that would be, I think, better description of what we are doing. Okay. So probably you ask what we're doing here, okay? So we learn a lot of things about random variable, right? Discrete random variable, okay? The thing is how we apply in the practice, okay? And here I'm trying to give you some example that often arise in application, okay? And you can summarize this application. Usually the random variable will look like certain way. There's some mathematical structure. There's some property that commonly used in application. Okay, so we study them because they have a lot of application. Okay, so that is the main idea. Okay, it will be something like, as I mentioned, right? There's your buffet. You're the restaurant owner. You're doing the buffet. How many food you have to prepare? How many customers are going to come in? Okay, do this kind of problem. Okay, it become more clear as we proceed. Okay, so don't worry. We'll go one by one. Okay. And you learn. Okay, the first one is pretty much we have learned, so it's not something we need to spend time on. It's called uniform distribution. Okay, what is it is each outcome is equally likely. Okay, it's more like classical way, and the support is just some number from 1 up to n. Okay, so I didn't put a number here. Maybe x1 is 1, right? It's 1. Say in the case of the die is 1 up to 6, right? And in the case of the pros and cons can be 0, 1, or 2 if you told twice, right? So just like a bunch of numbers, right? And where they're equally likely, right? And they're equally likely, okay? And this is the basic thing we have been doing, but there's not too much application, okay? Unless you think that a very special case, okay? So it's just there because this is what textbook say was uniform, okay? Uniform means each outcome, each number is equally likely. I think we can talk about, after this graph, we can talk about important things. So look at the graph, you have to draw the px, okay? And when I have the number is 1 up to 5, right? That means that they have the same height, right? Uniform means 1/5, right? When I have this guy is 1/3, right? So probably you would ask why we care about the graph, okay? And also the graph for every single distribution. The reason is being that what you're doing in the real world is you have the data, okay? Say suppose I want to know how many customers are coming in, right? Then I have coffee shop and prepare how many coffee, how many ice cream for today, right? Then in that case, I need to look at data, right? The data have I plot a bar graph, right? And the bar graph will tell us what should be the distribution look like, right? If I look at data looks like this one, then that's good, right? So suppose I'm the owner of an ice cream store, right? I was guessing there may be 5 customers coming in the upcoming hour, right? Then I need to say, I need to prepare food. Then I need to put them from the freezer to the fridge, right? For the upcoming hour, right? Then look at this table, and I guess then I know how much thing I need to put out, right? To unfrozen things. So that is, and then look at the historical data, right? Look at the graph, which one looks like, then this would be a good model to fit. Okay, so just to repeat, to summarize, why we care about this graph is from the data, okay, you would look like certain shape, okay, and you try to fit the model, which model would be fitting, what kind of random variable would fit. Uniform would look like this way, everything is flat, okay. If your data looks like everything is flat, uniform is a good one, okay. But hardly things are uniform, but sometimes the data is a lot, then uniform may be a good one, okay. And I think it's most fruitful to go to directly to this one. Probably we'll finish this one today, and then we'll do it the next tomorrow, on Wednesday. Okay. So it's this one. The name looks very weird, Bernoulli distribution. Okay. So you may ask what it is, and if you know history of statistics or mathematics, Bernoulli is a very famous family for mathematics, and in fact, one can consider they are one of the founding fathers of the probability. Okay, so this the first few guys that they are doing probability in the I think 1600. Okay, 15th to 16th century they do this. Okay, the first time they study this is they study a very simple thing. They focus on a random experiment only have 2 outcomes, either success or failure. Okay, you can imagine that this is a pros and cons, right? Head or tail. Okay, just 2 outcomes. Okay, and particularly they call one is called success, one is called failure. Okay, success probably P, and failure is 1 minus P. This is success, this is failure. Okay, and if P is 1/2, that's a fair con toasting, right? If P is more than 1/2, then it's likely success. Right? The simplest thing in this world, actually, we have been doing so actually a lot, is random variable, right? It's number of success, right? So success is 1, failure is 0. That's what it means, right? So that's why the support is 0, 1. Is that clear? Just only 2 outcomes, success or failure. success probability P, okay, failure is 1 minus P, okay, and we call number of success, okay, it's either 0 or 1, right? So that is that's the probability, right? That's what it means, right? And if you try to put in the probability function like this, right? X is 0 or 1, and probability is 1 minus P and P, okay? So basically what we are trying to do is there can be many outcomes in the random experiment. We're going to divide them into two parts. Either we call all this failure or success, right? That's how I do, right? If I have a quiz, right? I would say you pass, you get all the score. You don't pass, you get 0, right? I don't care whether you're above it or below it, right? Sometime, right? It's like this, right? Say you go to, I don't know, probably go to get a driver license, right? You may get 100 points, you may get 99, 98, doesn't really matter because all it takes is either fail or success, right? So that's simplify the sample space. Remember, random variable is a simplified sample space, right? Because there are many, many things, right? But you call success or failure, right? It doesn't really matter, right? Now, the question is, can we write this one, right? Can we come up with a nice function, okay, of P? So this is a nicer function, okay? This is just the simple way, a complicated way to say P0 is 1 minus P, P1 is P, okay? So either you love this guy, same as this guy, same as this expression, okay, same this expression. And in the next class, I will tell you why this is more convenient, but this is exactly this one, and I convince you why this is the case, because you have to know P of 0 is 1, okay, same as 1 minus P of 0 is 1, okay. So now why this would important, right? This learned from high school, right? Any number to go to the power 0 is 1 except 0 itself, okay. And the reason is being that if x equal to 0, right, P of 0, okay, is P to the power 0, okay, 1 minus P to the power 1 minus 0, okay, this is 1, okay, this is itself raised to the power 1, so that's 1 minus P, okay, and P of 1 is small p raised to the power 1, 1 minus P, 1 minus 1, this is P, okay. So this is how you end up with this expression, okay? And is it important? I mean, is it real? Yeah, it's real. I mean, when I learn it, it took me like 3 hours to see why this is true. I mean, why? I mean, suddenly this thing appear out of nowhere, and you will think, why you think about it this way? Okay, it will be more clear when we talk about binomial distribution. That will be much more clear later. But at the moment, it is. I mean, if you're still confused, probably some of you are, it's just this guy, okay? This is the guy we have, but we can write in a compact form in this way. And why we write this way is more convenient. It will be more clear when we talk about things in next one, okay? So what we left here is the mean and the variance, okay? So you can see the mean here is P, okay? And the variance is P times 1 minus P, okay? I think to calculate mean is P is not surprising, right? Because we already know that opposing a con is fair con, the mean is half, exactly P, okay? So in that case, in general, this thing generalized is if you have more likely success, suppose P goes to 1, right? It's very likely success, actually the mean is 1, right? If P go to 0, let's go to 0. It's linear. So the higher, right? The higher the P, the higher the number of success, right? Okay, I don't think that's surprising because if P goes to 1, then you repeat the experiment, and many of them is 1, and very few of them are 0, right? So it's linear to P. Now the difficult part lies on the variance is a little bit not that simple. It's actually this guy, okay? And these two actually have proof behind. You can look at the technical slide to show to show you why this is true. Right? Here I want to give you the explanation why they are true. Okay? How to get it? You can look at the proof, which we don't really require. Okay? But do note that what do you see from this P times 1 minus P? Okay? If you try to recall what you learned from the high school, maybe I have a whiteboard. Okay. This is P. This is P times 1 minus P, right? P is only 2, can only go from 0 to 1 because probability, right? Okay. And what is this function? Looks like when P is 0, this expression is 0, right? This is 0, right? And this is 1. Actually, it cannot go to 1, but when P is 1, this is also 0. Right? If you learn from the high school, actually, this is actually P minus P squared. It's a quadratic expression, right? Look like this. Okay, not very perfect. But you will see the maximum point is 1/2. This is 1/4. Okay, so why is it true? Okay, so remember, variance is looking at, you repeat this experiment many times. Okay, many times, P of time success, 1 minus P is failure. Okay, first to understand why we have these two, first is very simple. When P is close to 1, right, all of them are success. Okay, there's no variance. Similarly, if P is close to 0, all of them are failure, or most of them are failure, then you don't have variance at all, right? So why, the question is why the variance highest when it's 1/2? Okay, why is it 1/2 is the biggest variance to observe? Well, because actually you don't really know whether you have success or failure, right? And either you have, a lot of time is either 0 or 1, right? 0 or 1, a bunch of 0, 1, 1, 1, 0, something like that, right? And you do know that the mean of this is just expected value of x, right? When it's 1, it's actually 1/2. Okay, every observation is actually minus 1/2, right? And take square. So that's the maximum difference. You maximum difference you can get, right? Or you can imagine that it's either half of them are success, half of them are failure. That is the maximum difference you can expect, right? It's not equally distributed. It's a, one is either very big, one is very small. So that's why the biggest variances appear here. Okay, biggest is here. On both sides is smaller. Okay, I hope that would convince you that this is the case. Okay, and or I said here, when the extreme value, okay, then it's small, right? And your highest variance then is most uncertain. Okay. And the graph like this one, if P is set half, then the same height. And if P is less than 1/2, then look like this. Okay. And if P is more than 1/2, look like this. Okay. So that would be the graph looks like. And we will extend this to more than one trial next class. So that's the end for today. I will see you after your holiday. Okay. Have a safe hike.